Welcome to August 31st LeetCode Challenge. Find minimum in rotated sorted array. Suppose an array of length n sorted in ascending order is rotated between 1 and n times. For example, the array nums might become 1 all the way to 6, 7. Might become this array if it's rotated 4 times. It might become this array if it's rotated 7 times. Notice a rotating array from a index 0 all the way to a index n minus 1 times, rotating it 1 time in the array will result in a minus 1 all the way to a minus 0 to all the way to a at index minus 2. Given the sorted array nums of the unique elements, return the minimum element of this array. You must write the algorithm that runs big O of log n times. Okay, so this is basically we have an array that is was sorted, but it was rotated a couple number of times, and we want to find the minimum number that's in the array. All right, now how do we do that? Log n times. So say we're given this array, we rotate a couple times, say 4 times for the original, which is 1, 2, 3, 4, 5. Rotate 3 times, we get this array nums here. And we know from inspection, because it's small, that the smallest number is 1. So therefore the output is 1. Likewise, we're given this array here. The original array that was rotated 4 times was this array here. And then the smallest number in that array is index 0, which is 0. See, if we're given an array that's already sorted, for instance, right here, then the smallest array is the first index. So how do we go about solving those? Right, so we have the constraints here. Each integers are unique. So it's telling us the array was originally sorted, but it was rotated a couple of number of times. And we're looking for a small deflection from the point is increasing sequence. Small deflection. So it's telling us kind of like a divide the search space into 2. And so telling us to divide 2 pointers. And what type of search algorithm has log n times, which would be a binary search, because it has an inflection point, which is the midpoint, right? And it's telling us to look at all the elements to the left of the inflection point, if it's greater than the first element in the array, or look at the elements to the right of the inflection point, which is less than the first element of the array. So everything's kind of pointing towards a binary search, and so that's how we're going to go about solving this. So the first thing we want to do is find if there's only one element inside the array, then if the length of nums is equal to 1, or nums at index 0 is less than nums at -1. This is just to be absolutely sure there's only one element. So we're going to return the first element, or return the only element, I should say. Return nums at index 0. We're going to develop some pointers. Left pointer is going to be 0. Right pointer is going to be the length of nums minus 1. And then we're going to enter our binary search algorithm, which is going to be while left is less than or equal to right, we are going to find the midpoint, which is going to be left minus right minus left. No, it's going to be it's the average. Right minus left divided by 2. It's going to be actually floor division, or integer division. Okay, so a couple of conditions here. So the first thing we do is we check the edge cases, right? So if the length of nums is equal to 1, that means there's only one element in the array, then we return the first element. Or the length of nums at index 0 is less than the length of n minus 1, that means we also return the first index, right? we develop our left pointer, our right pointer, then we define our binary search function, which is basically the midpoint is left plus right divided by 2. Now, with just 3 things we need to check. The first one is an if statement that states that if nums at the midpoint minus 1 is greater than nums at the midpoint, so the number at mid is the minimum number, then we're going to return that number at mid. So this is the left side. Now we're going to switch to the right side. So if nums at mid it's greater than nums at the right pointer, we're searching on the right side because the smaller elements are located on the right side. And then we want to move our left pointer to be mid plus 1. Else, we are going to move our right pointer to be mid minus 1, because searching the left side, the minimum size on the left side. So while left is always less than or equal to right, we're going to run this binary search algorithm. Let's run this code and check to see if it's correct. Submit. Awesome. So this algorithm runs at big O log n times for time complexity, because the pointers are moving, right? They get less and less each time we search through the algorithm. And space complexity is big O of constant space, because we're only keeping track of the 2 pointers and we're only returning the index of the mid nums. Midpoint index of nums. Alright, that's it. Have a great day, guys.